Welcome to Stochastic Processes, Lesson 13. In this lesson, we'll go over problems and solutions to those problems concerning the lessons 1 to 12. So here's the structure. The format is that there's a problem stated on one slide, and then the solution is on the next slide. So it gives you a chance to pause the video and try the solution. You may need to go back to some of the previous videos to look up the different formulas. What is assumed? Every problem uses a result established in parts 1 to 12. Nothing new is needed. The lesson each one draws on is named at the top of the slide, so that'll kind of give you a hint as to what lesson you need to open up again and have a look at. And a note on arithmetic, answers are given as exact fractions where they are clean and to 4 significant figures otherwise. Problem number 1 relates to lessons 1 and 2 on transition probabilities. We're given a Markov chain with 3 states, 0, 1, and 2. This is the transition matrix. Then we have 2 problems. Find the probability of being in state 2 after 2 steps, given that you start in state 0. Then given that the chain starts in these states with the given probabilities, 1/2 in state 0, 1/2 in state 1, and 0 probability in state 2. Find the distribution after 2 steps. So if you want to give this a try, pause the video, and then I'll give you the solution on the next slide. So the trick here is to take the matrix T, or the matrix given on the last slide, and square it, multiply it times itself, and then these are the 2-state transition probabilities. So the probability of going from 0 to 2 in 2 steps, this is the row 0, and then going to state 2 is 1/8. Then to find the distribution after 2 steps, we need to multiply the initial probability distribution, P0, that we were given, times this here. So I did that. I multiplied it out, and there was the third component of P0 was 0, so we didn't, that's why there's only 2 row multiplications here. And then you just sum that up and you get this here. And so the probability of being in state 0 after 2 steps is 5/16. Probability of being in state 1 is 1/2. And the probability of being in state 2 is 3/16. And you can check this, they add up to 1. If you convert this to 8/16, then you can see it adds up to 1. Okay, and then I just put the answer down here at the bottom. All right, let's continue. Okay, problem number 2. This relates to gambler's ruin. That was in part 3 or lesson 3. A gambler bets $1 of a game. Each play is won was probability 0.4 and loss was probability 0.6. The gambler starts with $4, and when she reaches $8, she stops or she goes broke. In other words, when she has $0. So the game, the boundaries of the game are 0 and 8, and she starts in the middle with $4. Find the probability that the gambler is ruined. In other words, she goes to $0 before she wins 8. So if you look up the formulas in lesson 3, you know that you need to compute R. That's Q divided by P. So that's 3/2. Then A is the pot, so to speak, the stopping point if you win all the money, and then K is where you start. So our gambler started with $4, or whatever your currency is. Then the probability of ruin, given that you start with K equals 4, we use this formula here. So we put in 3/2 for R, 4 for K, and 8 for A. And then we just do the calculations. And the probability of ruin is 81/97. So fairly high probability of ruin. I have a second example on the gambler's ruin. This time we assume the game is fair, so P and Q equal 1/2. There's $1 per play, and this time the gambler starts with $20, and she plays until either she goes broke or she reaches $50. So find the probability of ruin, find the expected number of plays before the game ends. The probability of ruin is the formula for a fair game we derived earlier. I'm pointing to it here. So A is the total pot, $50. K is how much our gamblers started with, and then you divide that by A. And so the fair game ruin probability is 3/5 under the conditions of A and K that we were given. And then from part 4, we have the formula for the duration. It's given by this here, where capital A equals 0 and B equals A, so it's this formula. And we have K and A, so we just plug those in, and we have 600. So the probability of ruin is 3/5, and the expected duration is 600 plays. Problem number 4 comes from the lesson on random walks. A random walk starts at 0 and takes 100 steps. This is one-dimensional, so you either go left or right or up or down, but just one dimension. Each step is plus 1 was probability 0.6, and minus 1 was probability 0.4. So the bias is towards the right, so to speak, to the positive side. Find the expected value of x 100. In other words, where do you expect to be in it's step 100, and then find the standard deviation. Remember, that's the square root of the variance. And then find the probability that x sub 100 equals 20. So if we look up our formula from lesson 5, the expected value of the random variable xn is n times p minus q. In our case, n was 100, and p and q are plugged in here, and we get 20. So the expected position after 100 steps is 20 to the right. Then the variance is given by 4n pq. We plug in our numbers, we get 96. So the standard deviation is the square root of this, so roughly 9.8. So your expected position is 20 and plus or minus 1 standard deviation. So you'd be kind of expected to be between roughly 10 and 30. Count the number of up steps in order to solve the probability of being at position 20 after 100 steps. So the number of right steps minus the left steps would need to equal 20, right? So you have to take 20 more steps to the right than to the left, and then the sum of the right and left steps is 100, since we're asking the question for after 100 steps. So if you solve these two equations, you get r equals 60, and then we can plug that into our equation for the probability of being at step 20 or position 20 after 100 steps. This is 100 choose 60 times 0.6 to the 60 times 0.4 to the 40 power, and if you do this computation, you get a small number, 0.0812. So about a little over 8%. Problem number 5 involves first returns for random walks. So we have a symmetric random walk. That means the probability of going left or right is 0.5. and we start from 0, and we only take one step at a time. We have two problems. Find the probability that the first return to 0 happens at step 8. And then the question is a return to 0 certain? In other words, is it a probability 1 of returning to state 0? We have a formula for the first question. It's f sub 2n equals this expression here, where c sub m is the mth Catalan number, which I've listed here. And you start from m equals 0, m equals 1, and so forth. So we have 2n equals 8, right? We wanted to check for 8 steps. And the reason this is 2 and not just n here is because you can only return on an even number of steps. So that's why we derived the formula like this. So n equals 4. So it's 0, 1, 2, 3, n minus 1. We need c n minus 1. So that's this term here, 5. We plugged it into here, and we get what, a little bit less than 4%. Then we need less than 6a actually to compute the return probability. If you recall, we had this generating function, and if you put in 1 for s, you're basically summing over all the possible first returns. So I did that, and the equation for this, which we derived, was this here, 1 minus the square root of 1 minus s squared. So when we put in 1 for s, this becomes 0, and you just get 1, which means the total is the sum of every first return probability. And if that's 1, that means you definitely are going to return. So the state is recurrent. State 0 is recurrent. Problem number 6 involves classification of the states in a Markov chain. So we have a particular Markov chain here. It has 5 states. Rather than read through this, I'll just point to the diagram here. So you go from state 1 to state 2 is probability 1. However, state 2 can either go to 1 or state 3 was probability 1/2. And then 3 returns back to itself. So this is an absorbing state. Then we have this other 2 states. Clearly these are separate from the first 3. So if you're in state 4, you can go back to state 4 at the next transition was probability 1/2, or go to state 5 was probability 1/2, and from 5 you reflect and always go to 4 was probability 1. Okay, so the questions are: find the communication classes, classify each class as recurrent or transient. I copied our diagram from the previous slide. So you might be tempted to say there's just 2 classification classes here. However, that's not correct, because 3 is an absorbing state. So this is a class in itself. Once you go here, you can't come out of it. 1 and 2, you can go from 1 to 2 and then from 2 back to 1. So this is another class. And then 4 and 5, you can go back and forth between them. And so that's the third class. And of course, we can't get between 4 and 5 and anything in 1, 2, or 3. Okay, so that's the first question. Then the other question was which ones are recurrent and which ones are transient. From chain 2, the chain can move to 3 and never return, referring to this here. So 1 and 2 are transient, because there's not a 100% probability that you're going to come back to this to 2. And if you remember, the classifications pertain to all the states in a classification class. So the 1 and 2 are transient. 3 is absorbing, as I mentioned when I was actually stating the problem. So 3 is recurrent. 4 and 5 is closed and finite. And by theorem in part 7, this is recurrent. And you can kind of intuit to that. You can go between the two states indefinitely, and there's always a definite probability you're going to come back. Okay, so that's the answer. 1 and 2 are transient. The class just containing 3 is recurrent, and then the class containing 4 and 5 is recurrent. Problem number 7 is based on lesson 7 on recurrence and transience. We have this Markov chain. From state 1, you return to it in the next step with probability 1/3, and then with probability 2/3, you go to state 2. From state 2 with probability 1/2, you go to either state 1 or state 3, and once you hit state 3, you're absorbed and you return to it indefinitely. So that's what I've written here in words. State 3 is absorbing. Then 2 questions. Find the probability that you started here in state 1, that you eventually come back. And if that probability is less than 1, then the state is transient. So we're being asked to classify the state. In fact, it is transient, but we need to verify that. And then find the expected number of visits to state 1. I have the solution on this slide. I copied a few things down just to help you out. This is the Markov chain from the previous slide, and this was the definition of Fi, comma I. It's the probability that the minimum return time is less than infinity, and this is the definition of tau sub I. If you recall, this was a bit tricky to compute. In this case here, there's 3 different paths or types of path. In one type of path, you come back in the very first step and was probability 1/3. And what happens after that doesn't matter. We're only interested in the first return. So the first return of step 1 is probability 1/3. Then the first return is in 2 steps. You go out 2/3 and then back 1/2, and that's 1/3 also. So those are 2 classes of paths that start either immediately turning to 1 or going out to 2 and then back to 1. And that gives you 2/3 of the probabilities of having your first return less than infinity. Then the third case is you go from 1 to 2 and then from 2 to 3, and of course you never come back from that, and that's another 1/3 probability. So the 3 add up. All the paths are in one of those 3 categories, and what we're looking for is the probability that your first return is less than infinity. So you just want to add these 2. You get 1/3 and 1/3. You get 2/3. That's less than 1. And so state 1 is transient. And in fact, state 2 is transient because we proved that in a finite Markov chain, within a class, all of the states are of the same classification. And then we were also asked to find the expected number of visits, and we had a formula for that. It was 1/1 minus, in this case, F1 comma 1, and we computed that to be 2/3. And so you get 1 minus 2/3 is a third, and then you get 3. And then we also have a bonus. If you sum up all the probabilities of going from state 1 to 1 over n, you get 3, and that's because the expected value, this thing here, is equal to this quantity here. So you get 3 in that case. Okay, so just to summarize, the answer is F1 comma 1 is 2/3. State 1 is transient. State 2 is transient. State 3 is recurrent. Obviously, you can't come out of that. So once you're in there, you keep recurring. And the chain visits 3 times back to state 1 on average. Problem number 8 is about periodicity. We're asked to find the period of state 1. Let's just review the Markov chain quickly. So from state 1, you go to 2 with probability 1, and from 2 to 3 with probability 1. Then at 3, you can go back to 1 with probability 1/2, or to state 4 with probability 1/2, and then from 4 you always return to 1. So we need to find the period of state 1. That's our problem. So as you may recall, the period of a state is the GCD of the different number of returns. You can see here we go from 1 to 3, so it's possible to get back to state 1 in 3 steps. Then another possibility is 1, 2, 3, 4. We don't need to look any further because the GCD of 3 and 4 is 1. And even if we found other possibilities, which there are, they're going to be combinations of 3 and 4 steps. So the GCD is 1. The state is aperiodic by definition. Since the chain is irreducible by theorem 25, several lessons back, every other state is aperiodic. In other words, it has period 1. And then we just have a summary here at the bottom. The GCD is 1. This entire chain is aperiodic. Problem 9 relates to stationary distributions. I took the Markov chain from problem 1 at the beginning of this lesson. And the question is, find the stationary distributions for this Markov chain. Remember, that's the probability of being in each state in the long run. So we have state 0, 1, and 2. So we need to find 3 probabilities. And we call that row vector pi that has the stationary distribution. From lesson 8, we know the way to find stationary distributions. We solve this system of equations, which I've multiplied out here. And then there's a fourth equation, pi sub 0 plus pi sub 1 plus pi sub 2 equals 1. So from the first equation, we get pi sub 1 equals 2 pi sub 0. And from the third equation, we get pi sub 1 equals 2 pi sub 2. So we have pi sub 1 in both of these, which means 2 pi sub 2 equals 2 pi sub 0. So pi sub 2 equals pi sub 0. Then we plug these results into the equation where we have the sum of the pi sub 0 plus pi sub 1 plus pi sub 2 equals 1. So this is pi sub 2 is pi sub 0. It's this third one here. And then pi sub 1 is 2 pi sub 0. That's this one here. So we get 4 pi sub 0 equals 1. So pi sub 0 equals 1/4, which means pi sub 2 equals 1/4, and then pi sub 1 is twice that, it equals 1/2. So our solution is 1/4, 1/2, 1/4. You can double check by multiplying this times t, which I'm showing here, and you should get the same row vector, which we do. And just a reminder that what this means. So in the long run, you spend roughly 1/4 of the time in state 0, 1/2 of the time in state 1, and 1/4 of the time in state 2. I have sort of a review of lesson 9 before we get to problem number 10, and I also added a few items here. In lesson 9, we did some work to derive the probability x was greater than a, where x is this exponential function, and it's e to the minus lambda a. And then we also mentioned that the cumulative distribution, in other words, a probability less than or equal to a, is given by this. The sum of these two is 1, which makes sense, right? Either you're less than or equal to A or greater than A. So the total probability is 1. Then we have the density function, which I did not mention in lesson 9. The area under this curve gives you the probability. So you take the integral of this from 0 to A, you would get f of A. And if you took the integral from, say, A out to infinity of this, you would get g of A. So f of x is related this way. It's the derivative of capital F evaluated at x, or minus the derivative of g of x. And another thing I did not mention in lesson 9, but we'll need to solve the problem 10, is the expected value. There's two ways of doing it. The standard way is you take the integral from of x times the density function. And in this case, it would involve integration by parts. It's a little bit messy, but there's a simpler way. You can just take the integral of the survival function, and that's also equal to the expected value. So you take this integral here, and the antiderivative of this is just minus 1 over lambda times e to the minus lambda x. And then you evaluate that at infinity and subtract that evaluated at 0, and you get 1 over lambda. And so we'll make use of that when we get to problem 10. Problem number 10, as I mentioned, this is based on lesson 9. A continuous time chain holds in state 0 for an exponentially distributed time with rate lambda equals 3 per hour. What is the mean holding time? Find the probability that the chain stays in state 0 for more than 40 minutes. Given that it has already stayed 20 minutes, find the probability it stays a further 40 minutes. Again, we're referring to state 0 in item 3 here. For the solution, I gave you most of the information in the little reminder slide a few slides back. So the expected value is 1 over lambda. So that's pretty fast to do that. We just do 1/3 hours or 20 minutes. Then the survival function, which is what we want, what's the probability of staying in state 0 for more than 40 or more minutes? That's 2/3 of an hour. We just plug that in. So it's minus 3 times 2/3. So e to the minus 2, or about 0.1353. Then I guess C was a little bit of a trick question. Because of the memoryless property, we don't even need to do this here. It's 40 minutes is 40 minutes, regardless of how long you've already been in state 0. So you would expect the same answer, which is the case. Okay, so let's continue. I have I think a couple more problems. Problem 11 is based on lesson 10 on Poisson processes. We're given a Poisson process arrival at a counter with rate lambda equals 4 per hour. We have 4 questions. Find the probability of exactly 5 arrivals in 2 hours. Find the expected value for n of 2, as well as the variance. Find the probability that the first arrival comes after 30 minutes. A second independent stream arrives at 6 per hour. So lambda would be 6 in this case. When the streams are merged, what is the probability that the next arrival is from the first stream? You may remember we had a formula for this. Here are solutions. The first one was find P of n equals 5. So in other words, 5 arrivals in 2 hours. So we use this equation here from lesson 9. we have, less than 10. We have lambda t is, lambda is 4, t is 2 hours, so it's 8. So that goes in here and here. And then n is 5. And we do the computation, and the probability is 9.16%. Then the formula for the expected value and variance is pretty straightforward. It's just lambda t, and they happen to equal each other. So we just get 8. We proved in the lesson 10 that the inner arrival times were exponentially distributed. So we have this formula, and we were looking for greater than 30 minutes. So we have to convert that to half an hour. And then we have to multiply by lambda, which is 4. So we get e to the minus 2. And that's 13.53%, or just, if you wanted this decimal, I have it written out this way. Then the merging is fairly straightforward. The probability that the next arrival comes from the first stream is this formula. So it's 4 over 10, and the formula for the probability coming, the first arrival is from the second stream, is almost the same, except you have lambda 2 here, and that would be 0.6. Problem number 12 is related to lessons 11 and 12. We're told that we have an MM1Q, and it has an arrival rate of lambda equals 8 per hour, and a service rate of mu equals 10 per hour. So we're servicing the arrivals faster than they're coming in. Find the traffic intensity rho and say why the Q is stable. So that's the rho is the lambda divided by mu. Find the probability that the system is empty. Find pi sub 2, the long run probability of exactly 2 customers in the system, and find the mean number in the system. For the solution, we need to use some of the equations from lesson 11. I copied them over here. So we want to show positive recurrent, and it follows directly from rho being less than 1, but we can actually verify it using the formulas. So if you put mu over lambda, you get the reciprocal of this. It's a number bigger than 1. And so for i equals 1, you get 1 over rho, which is bigger than 1, and then for I equals 2, you get 1 over rho squared. That's also bigger than 1. Basically, you get a sum of numbers larger than 1. It's an infinite sum, so this goes off to infinity. That means the process is recurrent. And then this gives you positive recurrent. This needs to be less than infinity. You notice the now lambda is on top. So now you're just going to get, and it doesn't vary, right? Lambda and mu are the same for every value of n. So you're just going to get rho in here. And so the first term is rho, and then it's plus rho squared, plus rho cubed, and so forth. So you factor the rho out and out of the summation, and then you just have the infinite geometric sequence, 1 plus rho squared, 1 plus rho squared, and so forth, which is 1 over 1 minus rho. So this is equal to rho over 1 minus rho. And if you plugged in 0.8, you just get a finite number less than infinity. So that gives us the positive recurrent. Then we need to use that, what I just described in here, to calculate lambda sub 0. So it's 1 over 1 plus rho over 1 minus rho. And when you simplify that, you just get 1 minus rho. And we plug in our value for rho, we get 0.2. And then this is just 1 minus rho, and this here is rho to the k power. So this gives us pi sub k. And then we're at the actual question, well, what is the stationary probability for state 2? So it's basically this formula here, rho times this, in other words, this. So it's 0.2 times 0.8 squared, so it's 0.128. Okay, sorry for not jotting down all the details. It was just getting a bit long here, but you might want to just practice your summation of geometric series to verify what I'm saying. Then the last one is even a little bit more tricky. I'll explain to you how I got this. The mean, of course, is here, k times pi sub k. That'll give you the mean. The problem is you're going to get a series that's k times 1 minus rho times rho to the k power. And you need to take the derivative of the geometric series to get a formula for the sum of k times rho to the k here. And I can even give you a link to the where that formula is provided. And when you go through that calculation, and I agree, there's some work going from here to here, you get rho over 1 minus rho. And then once you're here, of course, it's easy. You're just plugging in the 0.8 for rho, and you get 4 customers. So that's the mean queue length. All right, so that was it. That was the last problem in this lesson. And that is almost the end of this series. I just have one more slide, sort of a conclusion. So we concluded our playlist of 12 lessons with the 13th lesson that covered a lot of what we had done before. Much of it was plugging in the formulas. I realized that was kind of straightforward. The last problem was a little bit harder. You needed to do some work with geometric series. Hopefully that gave you some practice. And the very last part where you needed to take the derivative of a geometric series, and that also converges as long as the term in there, in our case rho, is less than 1. So where to go next? Well, much of what's in these lessons are in my book. There's a section on stochastic processes, and the electronic version is freely available. I'll give you a link to that. And there's quite a few references in my book for other material if you want to go dig in deeper. Okay, so thanks for watching, and please give this a thumbs up if you like this video or if you like this series. Consider subscribing to my YouTube channel, and I do plan more videos. I think, well, what I'll do next are difference equations. I also have a chapter in my book on that, and I think I'll do a series on difference equations, some of which we used earlier on in these lessons. So thanks again for watching, and see you soon.